Hello everyone and welcome back. In the previous session, we were introduced to the parsers. In this session, we will start our journey of learning about the top-down parsers, starting off with the recursive descent parsers. So without any further ado, let's get to learning. Coming to the outcome of today's session, today we will first observe the top-down parsers. Thereafter, we will learn about the recursive descent parser with the help of an example. Now in the previous session, we observed the classification of parsers, didn't we? There, I told you that the top-down parsers can be classified into two different categories. That is, the top-down parsers with backtracking, which use brute forcing algorithms. On the other hand, we have the top-down parsers without backtracking. Now in this course of compiler design, we will mainly focus on the top-down parsers without backtracking. So from now onwards, whenever we mention about the top-down parsers, remember, we are talking about the top-down parsers without backtracking. So let's observe the top-down parsers now. Now in the previous session only, we came to know that the top-down parsers use the top-down approach of generating the parse trees. And in this particular approach, it uses the leftmost derivation, and the decision which it has to deal with is which production to use. Now, in order to construct a top-down parser, the context-free grammars should not have left recursion and any kind of non-determinism. That is, the top-down parsers, which is actually the top-down parsers without backtracking, because in case of top-down parsers with backtracking, those actually allow the non-deterministic context-free grammars. However, we are not interested in those. We are rather interested in the top-down parsers without backtracking. And in order to construct the top-down parsers, the context-free grammars should never have the left recursion. That is, if our context-free grammars have any kind of left recursion, we are supposed to eliminate that. And if you can recall, in the previous chapter, we already have learned the procedures of removal of left recursion. Furthermore, we also have to remove any kind of non-determinism. Now, if you recall, in the previous chapter itself, we also have learned the method of left factoring, using which we can eliminate any kind of non-determinism. So at the introductory level, this is all we have to know about the top-down parsers. Let's now observe the recursive descent parser now. The definition of the recursive descent parser is something like this. A recursive descent parser is a top-down parser built from a set of mutually recursive procedures or a non-recursive equivalent, where each such procedure implements one of the non-terminals of the grammar. Thus, the structure of resulting program closely mirrors that of the grammar it recognizes. So basically what we are trying to mean in here is, recursive descent parser is actually built from a set of mutually recursive procedures or a non-recursive equivalent. Now, what is a recursive procedure? These are actually the functions that we will be creating, which can be recursive, or a non-recursive equivalent can also be there. Now, what about the recursive procedures? These are actually the functions which can call themselves. Now, having mutually recursive procedures is not mandatory. We can also have non-recursive equivalent procedures. Now, the procedures will actually implement all the non-terminals of the grammar. Yes, that's correct. Basically, in a grammar, we have terminals and non-terminals. So, all the non-terminals in all the production rules of the grammar will have different procedures. And this way, the structure of the resulting program will closely mirror the grammar it is supposed to recognize. Now, this particular definition will be more clear with the help of an example. So, consider the following grammar having the rules. E can be rewritten as I, E prime or E dash. And E dash or E prime can be rewritten as plus followed by I followed by E dash or epsilon. So what we are going to do, we are going to take this grammar and we will try and build the recursive descent parser for that, and we will also observe how that works. Basically, we will try to observe that if this particular grammar is implemented using procedures, in that case, how can the recursive descent parser recognize an input string with the help of the procedures which mirror this particular grammar? So let's begin. Now, just now we have seen the recursive descent parser's definition. It said that for a given grammar, we will have to create procedures for all the non-terminals. So let's start off with this particular production. E can be rewritten as I followed by E dash. Now the function defining this will look something like this. Now as you can see, this is the procedure of E, and within the definition of E, we have this if statement which has a variable look ahead which is matching with I. Now look ahead is actually a variable which will be keeping track of the input stream. Now within this if block, we have another function called match which has the argument I. This procedure actually mirrors this I in this production rule. Now after this procedure match, as you can see, we are calling another procedure that is E dash, which basically mirrors the implementation of E dash in this production rule. Now just an FYI, we know recursive descent parser is actually a top-down parser without backtracking. And for the top-down parsers, we need a grammar which should not have any kind of ambiguity. Also, it shouldn't have any kind of non-determinism, and the grammar should also not have any kind of left recursion. Observe, these are actually right recursive grammars, as on the right hand side, the rightmost element is the non-terminal in both the cases. Now, if you remember when we started learning about recursion, we learned that with the help of right recursive rules, we can create procedures as such, where we can use the beta as a conditional statement, and within that block of the conditional statement, we can have alphas, which actually refrains us from getting into an infinite loop, doesn't it? Now let's deal with the next production rule, that is E dash can be rewritten as plus followed by I followed by E dash or epsilon. Now the procedure for E dash will look something like this. Observe, this is the procedure for E dash, and within the definition of E dash, we have two branching statements, that is this conditional if and the else. Now this if is actually for handling this portion of the production, and this else, which only states return, this one handles this portion of the production. So basically, E dash can be rewritten as epsilon is mirrored by E dash returning to the function whichever called it. Now apart from these two procedures, you can also see we have a procedure called match in both of the procedures. So let's define the match procedure for this. Now in the definition of match, as you can see, we are having the formal argument char c. Now this formal parameter will actually take values from these actual parameters. And within the definition of this match, we also have two-way branching, that is this if and this else. Basically the work of this if is we are going to take the look ahead and match it with the parameter which has just been fetched by this particular procedure. And if this matches, in that case, the look ahead will invoke the getChar function, which will fetch the next character from the input stream into this variable look ahead. And if it doesn't match, in that case, due to this else, we will get the output error. Now apart from these three functions, we will also have another function, that is the main function. Now coming to the main function, if you observe the definition of it, it just calls the function e, which happens to be the start symbol of the grammar. And once the entire execution of e is done, the main function will then check if the look ahead is the dollar symbol or not. Now why we are checking this? Because in all the parsers, whenever we use any input string, in order to denote the end of the input string, we use this dollar symbol. Basically, in the input buffer, we are going to place this dollar symbol by the end of the input string. You can relate this with the strings or character arrays. In case of those, we actually have the null to denote the end of the array, don't we? Similar to that, here also in order to denote the end of the input stream, we will use this dollar symbol. And if that look ahead matches this dollar symbol, we will print this output parsing successful. Now let me illustrate how these functions are going to work if we have the input I plus I. And observe, For this input, we already have placed the dollar at the end of the input stream. Now let's find out whether this particular input stream can be recognized using these functions. Now obviously we are going to begin from the main function. So we are in here right now. Now once we are in here, we will proceed further and we will get inside the main function's definition. Now see, in this particular line number 3, we actually are calling the function e, right? Now to be really honest, this particular grammar has been mirrored using these functions, isn't it? So whenever we will call a function, we will also try to create the parse tree simultaneously, which will help us visualize the entire procedure. So right now we are at the line number 3 of the main function, and here we are calling the function e. So to visualize this, we are going to place the non-terminal e in here. Now once this e is executed, thereafter we will come back to the line number 4, and we are marking this line number so that we can remember when we come back where should we start from. So basically this is just a marker. Now we just call the function e. So we will start from here, that is this line number 1. Now once we are at function e, that is the procedure e, we will get inside that. Now by the time we come to the line number 3, we are going to invoke this if statement. Look ahead is I or not. Now if you remember, I told you about the look ahead. It is actually going to keep track of the elements in the input stream, which in this case is keeping track of the first element of the input stream, that is I. Now remember, the scanning of the input stream will be done from left to right. So right now look ahead is actually keeping track of this I of the input stream, which matches this I, right? So we will get inside this if block. Now within the if block, in the line number 5, we are calling the function match I. And I told you earlier, whenever we will call a function, we will simultaneously create the parse tree. Here we are having I. Now invoking this function call will actually take us to this function. However, once the entire execution of this function is done, we will then come back to the line number 6. So we are marking it now. Let's now head towards the procedure match. Now observe, we send the actual parameter I. So now the character C is holding the value I. Now within the procedure of match, we are going to encounter this if statement. So look ahead equals C. What look ahead is holding for now? It is I. So look ahead is having I for now. And this C is actually the parameter which was fetched by this procedure, which in this case is I. Now since these two are matching, look ahead now invoke the getChar function, which will take the next character in the input string, that is this plus, and it will assign it to the variable look ahead. Now once this is done, we will return back to the procedure E, and specifically we will return back to the line number 6. Now in the line number 6, we are going to call the function E dash, which means from E, after we derive I, we are going to derive E dash. Now this one mimics the production rule. E can be rewritten as IE bar. So basically we are deriving IE bar from the start symbol E. Now once the E dash has been called and after the execution of E dash has been done, we will then return back to the procedure E, and specifically we will return back to the line number 7. We are again marking this so that we remember when we come back where should we start off from. Now we just invoked the function E dash, didn't we? So let's begin the procedure E dash. Now we will get inside the function E dash, and in the line number 3, as you can see, we are having this if statement where the look ahead is being checked whether it is plus or not, which evidently is plus at this particular time. So we can say this if statement will result positively, and thus we will be able to enter the if block. Now once we are in the line number 5 of the if block, observe, we are actually calling this match function with the parameter plus. Basically, from this non-terminal E dash, we are deriving the terminal plus. Now once the execution of this match is done, we will then come back to the line number 6. So we are using this as a marker for now. Let's now go to this match function. Now at this particular moment, this parameter c is holding the character plus. Now coming to this if statement, right now look ahead is holding the value plus, so it is having plus only, and c is also having plus. And since these two match, therefore look ahead will invoke this function getChar. That is, look ahead will now have the next character from the input stream, that is I. Now once this is done, we will then return back to the line number 6 of E bar. Now in the line number 6, as you can see, we are calling the match function with the parameter I, which basically means that from this non-terminal E bar, we are deriving the terminal I. Now again, once the execution of this match function is over, we will then return back to the line number 7 of the procedure E bar. Let's now head towards this match function. At this instance, the parameter c is having the symbol I because the actual parameter was I. Now currently the look ahead is also tracking I, so we are having I in look ahead and c is also having I. Now since these two match, this time look ahead will again invoke the getCharacter function. Basically it will now have the dollar symbol in it. So once this is done, we will then return back to the function e dash, specifically to the line number 7. Now in the line number 7, as you can see, we are going to call the function e dash itself. And this call means from the non-terminal e dash, we are deriving the non-terminal e dash once again. Basically, this one imitates the production rule. E dash can be rewritten as plus I e dash. Now once the execution of e dash is done, we will then return back to the e dash function itself, specifically to the line number 8. Now we are invoking e dash. So we will begin from here. Now coming to this if statement, observe, look ahead is plus or not, that is being checked. Now currently look ahead has the symbol dollar, so this will result in false. Therefore we will head towards the else and we will just proceed with the return. Now this means we are actually having the epsilon generated from this non-terminal e dash. Basically, we will return back to the function that was e dash itself, which actually called e dash, but we will return to the line number 8. Now the moment we return in this particular line number 8, see, by this time we have already gone through the if block. Therefore, we are not going to execute these two statements. Rather, we will end up in the line number 11. That is the end of the function e dash. So, we will wrap it up and then we will go back to the function that is e, which called e dash on the first place. And we mark the line number 7. So, we are coming back to this particular line, which again is the end of this if block. And with this, we are ending the function e as well. Now with this, we will return back to the line number 4 of the main function. Now here we are encountering this particular if statement. As you can see, we are checking whether look ahead is the dollar symbol or not. And in this particular case, it is the dollar symbol. So we will move towards the line number 5 and print that the parsing is successful, which is evident from the parse tree itself. Observe the yield. It is I plus I epsilon, which is nothing but the input stream. That means the processes which were created following this particular grammar, using these, we actually could recognize the input stream and thus we created the parse tree as well. And finally, we will get to the line number 6 of the main function, which will denote the end of the process. So this is how a recursive descent parser works. Basically, we will dedicate procedures for all the non-terminals, which is going to mirror the entire grammar. So in this session, we first observed the top-down parsers. Basically, we observed the top-down parsers without backtracking. Thereafter, we learned about the recursive descent parser with the help of an example. Alright people, that will be all for this session. From the next session onwards, we will start learning about the predictive parser LL1 parser. So I hope to see you in the next ones. Thank you all for watching.